Hello, everybody, and welcome to the Front Room. I'm your host, Nathan Rigoni. In this series, we're going to cover some of the basics of artificial intelligence and machine learning. The point of this series is to introduce most of you to the concepts that make up the basis of many of the technologies that exist in AI today. Break those technologies down into their components, and I'll try to explain from the beginning how we got here, what we use, and why. This should also help you understand what the concepts are, the limitations of AI, and what the future may hold for this technology in its use cases in industry. In each episode, we will choose one topic and we will break it down. I'm hoping to keep the episodes to less than 15 minutes. I hope that these episodes help, and I hope that you enjoy them. In today's episode, we're going to talk about hidden states, latent spaces, and neural networks. All right, let's jump into it. Okay, so this one's a bit more of a complicated topic. To understand why these are important, we first have to break down what it is. So as we transitioned in ML and we kind of moved forward, we started noticing that there was this capability that came around with a thing called AlexNet, and it kind of changed the way that we were capable of solving problems. And we were able to make things called neural networks where we could actually use functions that acted as nodes, and we could start essentially making these linear functions with linear combinations of values to be able to approximate higher order functions. And this is not an uncommon thing in math. Like you can take some, let's say, third order polynomial, and you can create a linear approximation of this third order polynomial. So what a neural network actually is it's a set of weights that are multiplied times the input values. They are then summed. The products of these weights times the inputs are then summed. And by doing this, what we do is we're actually creating this linear approximation of a much larger function by essentially adding more and more products of two values. This actually works really well with computers because computers are kind of built around being able to do linear algebra. And so by doing this, we kind of made the problem very suitable for computers. So the next concept that came out of neural networks was this concept of hidden states. So you can move from a single layer neural network that maybe has tons and tons of nodes to like a multi-layer neural network that has essentially layers that are in between your input layer where you put in all of your data. And if the input layer is the same size as the data that you put in, and when I say same size, like if you have 4 features, your input data layer is going to be 4 nodes wide. If you have 5 features, then it's going to be 5 nodes wide. So the concept of the output layer is also going to match the concept of how many things you need to get out. So like, let's say you just want a 0 or a 1 out of it to say like yes or no, then you're going to have 2 nodes on your output layer, a 0 or a 1. And that is the basic description of what you need in a neural network. Now, in between those input and output layers, you can have so many different layers. And I believe the last definition that I looked up for a deep neural network was essentially that it consisted of more than 3 layers. Any network, any neural network that has more than 3 layers, input, middle, and then output, is considered a deep neural network. So the concept of a hidden state or latent space is essentially looking at what is the state of the data as it's passing from input to output at one of these intermediate middle layers. So let's say if we have 4 layers, Then our first layer is the input layer. Our second layer is an intermediate layer. Our third layer is an intermediate layer. And then our fourth layer is the output layer. We could select one of the two intermediate layers in the middle in the sandwich here. We can select one of those and we can look at what is the value that is present at this layer when I pass in a certain example. That is called the latent representation of the input. And that is where we get the term latent space. It's also called the hidden state because it is not one of the states that is input that you would see, and it's not one of the states of output that you would see. Why is this important? Well, the first example of why this is important is comes about because we started using these deep neural networks to build things called autoencoders, where we would take in input information that was thousands of features wide, right? Like our input layer would be like, I don't know, 1,024 nodes wide, and we would compress that data down to something like 512 nodes. And then we would take and decompress it from those 512 nodes back up to the 1,024. And what we were doing by doing that is we were building a neural network that acted as a compressor. And in compressing the data, what we were doing was actually taking another path, like we've talked in previous episodes, towards generalizing data towards a problem that we wanted to solve. In the case of, and I'm not sure that everybody's familiar with this, but there is a large language model called BERT that acts as an autoencoder. It is a better autoencoder than the ones that came before it, one that we can mention, which are things like Word2Vec that you could Google if you wanted to look into that. But essentially, what we're looking to do is take our input data and generalize it by compressing all of the information into a lower dimensional space, like going from that 1,024 wide down to 512 or even lower. We could go, down to 128 or whatever. Like it just depends on what you want to do. But the point being is that when you do that, the model has to take a strategy of compressing this data in a way that makes it generalized. And to play out how this would work, I kind of want to do an exercise that is an anecdote of how we might recall a set of items or something like that from a list. So let's say that you have an assignment, and your assignment is to take down this list that's millions of examples long. And what you want to do is make a method so that you could memorize all of the items in the list. So for a computer, this is actually pretty easy. What you essentially do is you create a serial number for the item. And every time someone wants to know what, one of the items on the list is, you can just look it up by serial number. Like you'll say, oh, banana is this serial number, and then, I'll look it up. Or you can use a serial number to recall the item that's on the list. So what would be neat, though, is that if we could get some of the items on the list that were related to each other to be near each other on the list and have similar serial numbers. So one of the things that happens inside this hidden state or this latent space is that the model is learning to do that. It's learning to organize the lists. And let's say the lists could be literally anything. It is going to try to put fruit next to fruit. It's going to try to put animals next to animals. It's going to try to put inanimate objects next to inanimate objects. Things that are associated with tables, things that are like chairs and the table itself, are all going to go next to each other. And the reason for that is that in order to recall on that second side where you're decompressing things back from that 512 nodes wide up to the 1,024 nodes, to recall the data exactly, what you want to do is sort of strategize that certain areas in this 512 string, you want those 512 string serial numbers to be close to each other if the items are related. Why would that strategy work? Well, let's say that someone gives me something and it's a table, right? I want to make sure that when I get things that are related to tables, that I reduce the space that I am trying to recall from to only things that are table related. Even if it's a guess, I want to make sure that all table related things are in a separate space. This actually helps me to generalize and to preserve a lot of information when I don't have a lot of space to store it. And that's kind of what's going on inside of a latent space or a hidden state. So, why would this be important in AI and machine learning? And why would this be important in the application of AI and machine learning? So, when we comes to something like natural language processing and the use of large language models or LLMs, we sometimes use these things to do what's called topic analysis, or we sometimes use these things to do what's called latent space analysis, which is essentially taking a data set that we don't know a lot about and analyzing it by putting it into the large language model. Let's say I have a bunch of recipes, right, that I want to organize. I'm going to dump all my recipes into the large language model. And I'm going to analyze those recipes using the hidden space or the latent space that that large language model puts them into in order to organize them because it's built to do compression and decompression. This means that in that hidden state or that latent space, recipes that are similar to each other or involve making the same thing, like cakes and cookies and roast and fried potatoes and things like that, they're each going to be in separated spaces that are nice and well organized for things that are related to them. So all the cakes are going to be in one space, all the roasts are going to be in one space, cookies will be in a different space. And this is useful because now what I can do is I can use the autoencoder and its hidden state and its latent space to organize my data automatically. So to summarize and come back to essentially defining what these things are, a latent space or a hidden state is just essentially taking the current value of some intermediate layer in a deep neural network, usually an autoencoder, and looking at its state whenever we give it the input of some particular item. And this is always done after training the model because we need the model to organize that latent space first. So a hidden state and a latent space are essentially the same thing. One last concept that makes the hidden state and latent space important is that we can also use them to dissect what's happening inside the model and understand why it gives the answers that it gives. In large language models, this is a bit more complicated, and I'll cover that in a later podcast as of why. But essentially, what it boils down to is that this hidden state can give us inclinations as to why the output is what it is, and how things are organized in the mind of the model, and how it likes to think about things when it's deciphering the input data that we give it. I hope this information has been helpful, and I hope that you join us for future podcasts. Thanks for listening. You have been listening to The Front Room. The Front Room is written, recorded, and produced by me, Nathan Rigoni. If you'd like to know more about what our company does and what it could possibly do for you, you can reach us at nathan.rigoni@phronesis-analytics.com. We'd like to thank you for listening and have a good day.